Hello Year 10. Today's lesson is a revision lesson followed by a test. We've done 6 lessons about energy, some of them in class, some of them online. I'm going to spend today's lesson going through and reminding you about all those key ideas once again, and then afterwards, if you need to, replay it, make some notes, and then complete the test. So here are some basics about energy. The definition of energy is the capacity to do work. The unit of energy is the joule. The law of conservation of energy is this, and you must learn this. It's very, very important. Energy cannot be created or destroyed. It can only be transferred from one type to another. So that section there, you should write that down and learn it. So energy can be stored or it can be transferred. So here is a list of 8 different energy stores and 5 different energy pathways. Now, a pathway is another way of saying a transfer pathway. Okay, you need to learn these different energy types and which ones are stores and which ones are pathways. One thing to point out here is that sound and light are sometimes grouped together and sometimes called radiant. Okay, together, or often separated as sound and light. Okay, so please learn those different lists. So let's move on to kinetic energy first of all. Here's a picture of Usain Bolt, who at the time was the fastest athlete on Earth. He has lots of kinetic energy. All moving objects store kinetic energy. The faster the object moves, the more kinetic energy they store. The equation for kinetic is given down here. EK, that's energy kinetic, equals 1/2 times the mass times the velocity squared. Something to draw your attention to here is the square. Okay, this part here, students often forget to square the velocity. Right, so make sure that you use your square button when you're using this formula. So let's practice an example. Okay, so let's work out the kinetic energy of this bus. So I'm going to write the formula down. EK equals 1/2 times the mass times, it's not very good pen this, velocity squared. Okay, sorry about my very poor writing. So EK equals 1/2 times the mass, which is 12,000, times the velocity squared. Now we have to use the meters per second here. Okay, so it's 22 squared. Now I would use a calculator to do these. I'm just going to get my calculator. Okay, and we will type the numbers in and hopefully we'll get the correct answer. So let's have a go. Get my calculator ready. 0.5, which is 1/2, times 12,000 times 22 squared equals, according to this, 2,904,000 joules. I could write that as kilojoules. I could write down that's 2,904 kilojoules, and I'd have to divide the previous answer by 1,000 to convert to kilojoules. Okay, so there's an example. You will have to do something like this in the test. The next type of energy is gravitational potential. Now, if you look at the picture up here, we've got somebody who's jumping off a cliff into the sea, so they're up high. They've got lots of gravitational potential energy. So objects which are high up above the surface of the Earth have a lot of GPE. The higher they are, the more GPE they have. Here's the equation. This is a more straightforward equation. EG, which is energy gravitational, equals mass times G times H. So M is the mass, G is gravitational acceleration. You can take that to be 10, and H is the height. Okay, so we're going to practice using that equation. Now here is a rather silly picture of an elephant on a beach ball. So let's work out the gravitational energy. So it's Eg equals m times g times h. Okay, we're told that the mass of the elephant is 6,000 kilograms. G is 10, and the height, now the height of the center of the elephant above the ground is 2 meters. So the gravitational potential energy, let's multiply that lot together, 6,000 times 10 times 2 is 120,000 joules. And again, I can convert that into kilojoules by dividing that by 1,000, so it's 120 kilojoules. Okay. Again, you will have to do something like that in the test. 120,000. Okay, the next one is elastic potential energy. Elastic potential is stored in anything which is stretched, so a spring which is stretched or compressed. So a rubber ball, a tennis ball, or anything stretched like a spring or a rubber band, all of these things contain or store elastic potential energy. The more it is stretched or compressed, the more elastic energy it has. Here is a formula. It looks a bit like the one for kinetic energy, so you have to be careful that you don't get these confused. That's why it's so important to learn these equations. So EE, well, energy elastic equals 1/2 times K times E squared. K is the spring constant, which is how stiff the spring is. E is the extension. So we've got to measure the spring constant in Newton per meters, and the extension must be in meters. So beware of that. You may need to convert an extension in centimeters into meters first. Okay, here's another silly example. Let's work out the elastic potential energy stored in the pogo stick. So E equals 1/2 times K times E squared. Okay, so E equals 1/2 times, now K is the spring constant. This one is a very stiff spring, 200. And the extension here is in meters already, so it's 0.2, and that's squared. Okay, so let's work that out using our calculator. 0.5 times 200 times 0.2 squared equals 4. After all of that, it's only 4 joules. There's no point in converting that into kilojoules. 4 joules is fine as an answer. Right, let's have a look. Yep, 4 joules was correct. Let's have a look now. With springs, you have to work out the extension. Now, the extension is not the same as the length. And you can see down here, here is the extension. So to work out the extension, you have to subtract the original length of the spring from the new length. And here is the equation for that down here. Okay, so again, it's another small equation, but you need to learn it. To work out the extension of a spring, you subtract the original length from the new length. Okay. Work done is not an energy store, it is a transfer of energy. Okay, so it was one of the pathways that we looked at the start of this video. In fact, you can replace the word work done, with the expression energy transfer. Work is done whenever a force pushes through a distance. Okay, the distance is in the same direction as the force. So pushing a heavy trolley, supermarket trolley, you're doing work. Lifting a heavy box off the floor, you're doing work. Any of these types of situation, like the crane, for example, the crane is doing work. It's also transferring energy. We'll talk about that in a bit. So to calculate how much work is done, very simple. Use this formula. You multiply the force by the distance. Work done is measured in joules. Force is measured in newtons. The distance is measured in meters. Here's an example. Okay, we've got 5 questions to ask about this situation. We've got a person pushing a bin. Okay, so the pushing force is 400 newtons. F equals 400 newtons. Okay, the distance is 5 meters. Who or what is doing the work? Well, the man is. Yeah, who or what is having work done on it? The bin. Which store does the energy start as? Well, the energy in the beginning was stored as chemical inside his body, and it ends up as heat because the bin, as soon as he stops pushing, the bin stops moving, and all of that chemical has become heat energy. How much work is done? Well, let's use the formula. Work done equals force times distance. So the work done equals 400 times 5, okay, which is 2,000 joules. So what we can say here is that 2,000 joules of chemical energy has been transferred to heat energy. Oops, it's changed color. To heat or thermal, sometimes called thermal energy. Okay, right, let's move on. Okay, power. We've got two power lifters here. Power describes how quickly energy is transferred from one place to another. So a powerful person can do a lot of work in a very short space of time. That's what these two athletes are doing. They're going to do a lot of work. They're going to lift those heavy weights upwards in a very short space of time. Power is measured in the units of watts. Okay, so it's not joules. 1 watt is equal to 1 joule per second. The formula is power equals energy transfer divided by time. You could also write that as power equals work done over time. Okay, the two things are equivalent to each other. Right, here's an example for us to practice. So a broken down car is being pushed to a garage. Okay, work out the driver's power output if it takes 1 hour and 45 minutes to push his car 2 kilometers with a force of 900 meters. So there's a few stages to this. First of all, let's convert. Stage 1, convert units. Okay, so we've got 1 hour 45 minutes. Time equals 1 hour 45 minutes. Now that we can't have that. It needs to be in seconds, right? So if I was to work out how many minutes that is, first of all, that's 60 minutes in 1 hour plus 45. That's 105 minutes. There are 60 seconds in each minute, so 60 times 105 equals 6,300 seconds. That's the time in seconds, okay? The distance is 2 kilometers, so that's 2,000 meters. Got to be in meters. The force looks good. That's 900 newtons. That's fine. So these are now all in the correct units. So power equals work done over time. Work done is force times distance. Force times distance over time. So it's 900 times 2,000 on the top divided by 6,300. So let's work that out. 900 times 2,000 divided by 6,300. And the answer is 28. Well, I'm going to round it up to 28.6 watts. Okay, so that means every second this driver has to produce, every second he has to produce 28.6 joules. And if he does that for 1 hour and 45 minutes, he will successfully push the car to the garage. So he's got a lot of work to do. Okay, let's move on. Okay, another key concept in physics is useful and wasted energy transfer. Got two examples here. We've got a candle. Now, the energy is stored initially as chemical energy in the wax. When we burn the wax, some of the energy is transferred to light and some energy is transferred to heat. Light is useful because we lit the candle to produce light, but a lot of energy is also wasted as heat. Okay, so what we've got here is we've got the input energy. Sorry about my very poor writing, it's not easy to write with this pen. And then we've got useful and wasted. Let's have a look at the TV underneath. The input energy is electrical. The useful output, in fact there are two, because we want the TV to produce light and we want to hear it. So light and sound are useful, and heat is wasted, your TV warms up. Okay. So with this in mind, we can start to think about efficiency. Efficiency tells us how much energy is usefully converted. So going back to the TV here, if it will let me, won't let me, never mind, because I'm recording. If all of the electrical energy was converted to light and sound, then it would be 100% efficient. But some energy is wasted as heat, which makes the efficiency less than 100. Okay, you need to learn this equation. There are two equations. You can use energy output on the top and energy input on the bottom, or you can use power output on the top and power input on the bottom. Let's do an example. Okay, so first of all, we've got an example at the top that's been done for us. We've got a handheld gaming device, very old-fashioned now. The input is 275 joules. And then we've got three outputs. We've got light, sound, and heat. Now, the useful, well, we do want light because we want to see the screen, and we do want to hear the sounds coming off this game machine, but the heat is just wasted. Okay, so what we need to do here, let's calculate. All right, efficiency equals useful energy output total energy input. Okay, so efficiency equals 75, because that was light, plus 90, that was sound, divided by the total input, which was 275. So 75 plus 90 is 165, divided by 275 equals, using a calculator, 165 divided by 275 equals 0.6. Now, we can leave the efficiency as 0.6, that's a perfectly good answer, but sometimes we multiply that by 100 to get a percentage. You don't have to do this, but sometimes the question will ask you to do that.